All right, week 2 for lab 4, the chemical kinetics lab. Last week we talked about mostly issues that had to do with actually collecting the data. This week let's talk about the data analysis. So as before, this is the chemical reaction that we're measuring. This DNCB reacts with piperidine to form this yellow product DNPP and a piperidine left over, so 2 piperidines get used up for every 1 DNCB. The question is, once we've collected the data, how do we interpret that data? And the answer is that we want to build, the very first step in interpreting any kinetic data is to build some kind of kinetic mechanism, basically a kinetic model for what's going on. And that depends on chemical intuition, chemical insight, basically experience in what kinds of processes can occur in a chemical reaction. So let's go through the potential or the suggested model for this chemical reaction. The first step is thought to be an attack by the piperidine here on the positively or partially positively charged carbon that's bonded to that chlorine. And then that chlorine gets displaced. The piperidine basically replaces the chlorine and leaves behind a chlorine and a hydrogen, which then form an HCl, which then react with the piperidine HCl. We'll see all those steps in the overall mechanism, but this is thought to be the first step. It's this nucleophilic attack by the piperidine on the carbon atom that's bonded to the chlorine. In the standard way, the standard mechanism by which these kinds of things happen, the attack here gives rise to an intermediate. That is, an unstable molecule that hangs around only for a short period of time and decays one way or another by one of several different routes to more stable products. The intermediate in this case is a sort of semi-bond that forms between the piperidine and the DNCB. And notice that if we think of this as being a double-bonded, well, not really double-bonded, but an aromatic ring here, then this carbon here has 5 bonds in this intermediate. And notice also that the nitrogen here has 4 bonds in this intermediate. So it's an unstable species. Stable carbon species essentially never have 5 bonds. Stable nitrogen species, or at least the most stable ones, don't have 4 bonds. So this is something that only hangs around for a short period. It decays away then to other species. What are the possible ways in which it can decay away? Well, one way is that it just goes backwards, right? This interaction or this reaction between DNCB and piperidine forms the intermediate. The intermediate can just break back down and form DNCP and piperidine. I say here that this formation reaction should be slow, right? Because this is not a stable species. It ought to be at higher energy than the reactant species. And that means it ought to take some trouble. You're going uphill and going from the reactants to this intermediate. And it ought to be slow, therefore, to form that process. And that's why we say that we guess that this step is slow. And the breakdown process ought to correspondingly be fast, partly because, it's a downhill move from the intermediate back to the reactants, but also because the equilibrium constant for the formation of this intermediate ought to be small, right? It's the concentration of intermediate over the concentration of the reactants, DNCB and piperidine, and we expect there to be not very much intermediate at any one point in time, which means this equilibrium constant ought to be small, but that equilibrium constant is also the ratio of the forward reaction, that is the formation of this intermediate, over the backward reaction. In other words, this ratio K1 over K minus 1, which is the equilibrium constant, that ought to be small, which means that the backward reaction ought to be a lot faster than the forward reaction is. All right, so that's easy. We form the intermediate, and then we allow it to break back down. But the formation of the intermediate can't be the final step, right? Because we have to get to the product. We haven't got to the product yet. We haven't got anything that forms a product yet. So what do we do next? Well, if this is the intermediate, we notice that this atom and that atom, if they were to break their bonds and come off, could form a nice stable HCl molecule. And remember that this is all happening in organic solvent. It's not happening in water. So this HCl molecule doesn't come apart it doesn't come apart very much anyway, like it would in water. It stays as an HCl molecule. That means there's an HCl bond in there, a hydrogen to chlorine bond. And that means this is a downhill, or this is a favorable step, right? If these two guys form a bond with each other, that's a favorable step. So basically we can eliminate this HCl from the intermediate, and that does give us the product. So that's another route by which, this is I here, this is the intermediate, that's another route by which the intermediate can go away. It can reverse and go back to reactants, but it also can go forward and go on to products. When it goes on to form a product, it forms this HCl molecule, but also in solution, there's more piperidine. Piperidine is a base. It can react with this HCl molecule and form this protonated piperidine, piperidinate, I guess you'd call it, molecule or ion. And so that's also a step in the process, and I'll come back to that. But that's not the only route by which the intermediate can break down. It can break down to go back to reactants. It can break down to go forward to products. It can also be attacked by another piperidine, shown here, acting as a base to pull off that hydrogen, leaving the rest of this molecule unstable, allowing the chlorine to come off as a Cl minus. And so that's another step by which the intermediate can decay. So it can go backwards to reactants. It can go forward by reaction with piperidine itself. It can go forward just by breaking down spontaneously to products and either PIP-HCl or HCl itself. And then finally, the PIP in solution can react with the HCl and form PIP-HCl. So overall, that gives rise to this 5-step mechanism. Two steps here, 1 and minus 1. 2, 3, and 4 are the remainder of the 5 steps. And that's the hardest part of the whole business of interpreting a chemical reaction, is coming up with a plausible mechanism like this. And so we've done most of the work, and there is no hard and fast set of rules for how you come up with a mechanism like this. It depends mostly on chemical experience. But once you have that, then the next stage is to, once you've written down these elementary reactions, the next stage is to analyze this reaction mechanism in order to make testable predictions that we can compare to experiment. So the next part of the process, well, here's something that helps to analyze that mechanism. We can write the mechanism down as sort of a flow diagram like this, where DNCB goes to intermediate either by reacting with piperidine, and then the intermediate can go either back to reactants or forward by reaction with piperidine, or forward by just breaking down all by itself. Those are and then once it's broken down into DNPP and HCl, the HCl can react further with the piperidine. So that's the same 5-step mechanism we talked about earlier, but written out as a sort of flow diagram. And that helps it to understand, to see how things are kind of working with the mechanism. One thing that's important to notice in this, in both of these things, this step here and this step here, is that the formation of the initial intermediate is always likely to be slow, and that's going to be true for almost every chemical reaction, no matter what goes on afterwards. All right, so that's our mechanism. Now let's start analyzing it. The beginning of the analysis is to use these elementary reactions to write a set of rate equations. And now, since I imagine that many people in the class haven't written these kinds of rate equations in at least a long time, or maybe even ever, depending on what exactly was taught in your earlier classes, let's write down these rate equations and see how that's done. So I'm going to cut and paste these rate equations, and we'll write them down. So I mean, this shouldn't be magic, right? Let's just write down what these guys are. Let me start a new page here. So let's see where those rate equations come from, and then we'll see how to organize them. Notice that there's a lot of rate equations, right? There's 1, 2, 3, 4, 5, 6 rate equations, and none of them is actually a simple thing. And how to analyze a complicated thing like this isn't at first glance obvious. And so seeing how that works out in this particular case is helpful, is instructive. So let's go through it from the beginning. So first of all, there's one rate equation for every chemical species in our mechanism over here. Let's write down what the chemical species are. First of all, there's DNCB. That's a species here. There's piperidine. There's this intermediate. There's intermediate piperidine. Then there's DNPP. And then there's PipHCl. There's HCl itself. 1, 2, 3, 4, 5. Yeah, HCl itself. And I think that's it. Everything else is something I've already written down. So those are our 6 chemical species that are present anywhere in this overall mechanism. There's going to be a rate of change for every one of those chemical species, and that's what these rate equations are. They're equations expressing how each of these chemical species changes with time. So there always will be one rate equation for every chemical species that exists in the overall mechanism. So let's write them down. First of all, let's write them. Well, I don't think we'll write them all down because it will get a little tedious, but let's write down the one for, let's write down the one for the intermediate here. We can let's write down the top 2. So let's start with DNCB. So the rate of change of DNCB dt is equal to, let's see where DNCB appears. It appears here, it appears here, and it appears as a product coming back from here, right? So this is really 2 equations here. It's not just one, so it appears sort of twice because it appears in each of the 2 equations. So DNCB then, sorry, that's not DNCB over here. Sorry, it really only appears then here. That's the only place. Yes, all right. So there's just 2 places where DNCB appears, and that means there'll be 2 terms, one from each equation in which DNCB appears in the rate equation. In the first case, going forward for the forward reaction, DNCB will be equal to the rate constant for that reaction, K1, times the concentration of DNCB, because it's a reactant here, times the concentration of piperidine, because that's also a reactant here. And there will be a minus sign on that, right? Because DNCB appears as a reactant and so is disappearing. Its rate of change will be negative. Going back the other way, let me just write that out. Well, no, let me leave it as it is. the rate at which dNCB appears will be equal to the rate constant itself, k to the minus 1, times the concentration of the only reactant when we're going backwards, which is I. And so this accounts for the creation of dNCB by the dissociation of the intermediate. This accounts for the destruction of dNCB by the formation of the intermediate. And those are the only two processes that affect dNCB. And so that's that first equation that we see, that first rate equation there. Now let's write down this more complicated one. This is the most complicated rate equation in the whole thing. And so let's see how that works out. So we're writing the rate of change of the intermediate with respect to time. And now we go looking through the mechanism. Let me get rid of all this crap. First, we go looking through the mechanism for where the intermediate appears. It appears here, it appears there, it appears there. And notice that appearing here, again, this is two chemical reactions, so it's appearing for the forward reaction and disappearing for the backward reaction. Since it appears, therefore, in 4 of the different steps, there'll be 4 terms. Notice the 4 terms here, accounting for each of the processes that either causes the intermediate to appear or disappear. And we just go through those 4 terms one by one. So for the formation of intermediate, it will be K1 times dNCB times pyridine, right? Second order reaction. For the destruction of the intermediate, going back the other way, it'll be K minus 1 for the backward reaction times I itself. For the destruction of the intermediate by this elementary step, it'll be K2, the rate constant for this reaction, times I times pyridine. And finally, for the last way in which the intermediate can disappear, it'll be K3 times just I itself. All right, so we can go on and write down in that same way, using the same ideas, same principles, same logic, and write down all of these equations, these rate equations, for all 6 of the species that are present in the chemical reaction. All right, so that's where these guys come from. Now let's, this represents 6 equations, 6 differential equations and 6 unknowns. They can be solved. All these things can be solved for. And we would get the best possible answers by doing that out rigorously. You'd probably have to use a computer. But if you want to understand what's going on, it's usually of only sort of secondary importance to solve a complicated set of rate equations like this. It's usually kind of a set of rate equations like this is so complicated that it's usually hard to tell, even when you're solving, it's kind of hard to tell what the solution is really doing. So instead, let's go back and analyze this set of rate equations by making some further approximations. The very first approximation is something called the steady state approximation. It's an absolutely standard thing. And in the steady state approximation, we assume that the chemical reaction is going steadily. That is, we're not building up concentrations, we're not decreasing concentrations. The intermediate I has been created in the first part of the reaction. Later, when the reaction starts to run out of reactants, the intermediate concentration will decline, but in the broad region in the middle, in the broad range of time in the middle, we assume that that intermediate concentration will stay more or less steady. And so we make the approximation that at steady state conditions, in the middle part of the reaction, the intermediate concentration, the rate of change of the intermediate concentration will be approximately 0. That's not a rigorous statement. It is an approximation. But it's an extremely useful one, and it's one that can usually be made. Almost every mechanism has an intermediate, at least one intermediate. This mechanism is actually kind of unusual because it has only one intermediate. Lots of mechanisms have multiple intermediates. And then it's possible to set all of those intermediate concentrations, their rates of change, to zero, and that usually helps simplify big systems of equations like this an enormous amount. It helps in this case too. So we're going to make the approximation that the rate of change of the intermediate concentration is approximately equal to zero. Here's that rate equation that we had from above. Here it is, that one. And so we're setting that equal to zero, and then we're going to use that to solve for what this steady state intermediate concentration is. Setting this equal to zero gives us that the intermediate concentration is this expression, which doesn't mean a whole ton yet, but it does allow us to eliminate one variable from our set of 6 variables, right? We now have approximately, at least, an expression for how this intermediate concentration depends on all the other concentrations. We had 6 variables to start with. Now we've eliminated one. We only have 5 left. We are mostly interested in the rate of change of the product, the yellow product, the DNPP, because that's the quantity we're actually monitoring, right? It's the concentration of the DNPP versus time. That's what we're actually measuring in our experiment. And so let's look next at the rate equation for DNPP. Here it is. It's the next equation actually in our list after the intermediate one here. There it is. Let me copy it down. So copy it down here. Well, here it is. I don't really need to copy it. That's it. And notice that the intermediate appears here and here in the rate of change for DNPP. And now we can substitute our new steady state expression in for I here and I here. And if we do, then we get this new expression, which is still pretty complicated, but now doesn't depend on this funny intermediate anymore. The intermediates are important, but they very often are very hard to measure because they're usually not present in appreciable concentrations, and so you can't really measure them directly oftentimes. But you can often eliminate them from your chemical reactions using the steady state approximation. That's the general route that we've adopted in this case. So we eliminate these funny intermediate concentrations. That gives us this new expression, which in principle, it's still pretty complicated, right? But in principle, it tells us how the DNPP concentration changes with time, basically how it builds up with time. It's the derivative of the DNPP concentration versus time plot, right? This equation here gives us the slope of this curve. But it's still pretty complicated. We'd like to make it simpler. And in order to make it simpler, we notice that in this whole part of the expression here, this front part, what's in the numerator here is almost the same as what's in the denominator. If this k to the minus 1 here weren't there, these two guys would, this top and bottom would cancel, and we just get a big 1 in front here. And that leads us to look and see just how big this k to the minus 1 is. Is it significant? Is it something we have to worry about? Or is it small compared to what's left in the rest of this expression? If it's small, then this whole front part would be equal to a 1, and that would really simplify things. So let's look at that. K to the minus 1 is the rate constant for the backward reaction. Once you form the intermediate, you can go back to reactants, right? It's one of the steps we talked about quite a bit earlier. What if this k to the minus 1 is really small? In other words, this step were slow compared to the actual process of going on to products. what happens, what that would mean is that once you form this intermediate, there's a strong tendency for the formation of the product rather than going back to reactants. Once you get to the intermediate stage, it almost always goes forward to products by one route or the other, and rarely goes back to reactants. We don't know if that is true to start with, but we know that if we make that approximation, we're going to simplify things a great deal. So let's make it and see. Let's make the approximation, see what we predict on the basis of that approximation, and then see if that matches experiment. If it does, then we have reason to believe that the approximation was good. If we do that, then we can neglect this k to the minus 1. We can neglect this compared to these guys, to this stuff, and that makes the top and bottom the same. That means this whole term becomes a 1, and we get, finally, that with these approximations, the rate of appearance or disappearance of DNPP, the yellow product, is approximately equal to just one rate constant, K1, and it's this rate constant right here. It's the rate constant for the formation of the intermediate, is proportional to just the concentration of the two reactants, DNCB and piperidine. That's now a pretty simple system. All the other 5 rate equations have now disappeared. We got rid of this one because by making the steady state approximation, and now all these other ones don't matter anymore because we boiled things down to just one rate equation that matters. The only thing we can actually measure is the DNPP concentration, and we boiled the rate equation for that one down to this nice simple second order rate equation. All right. So that's how we get to this point. And from this point on, we're basically going to be analyzing this differential equation, right? This is a differential equation, a diffEq. We're going to be solving it, using that to get DNPP concentration as a function of time, and then comparing what's predicted by the mechanism with what we actually measure. All right. To do that, there are these 3 cases. First of all, there's the general case where there's no necessary relationship between the initial amounts of DNPCB and the initial amount of piperidine. In that case, there's no further simplifications we can make. We just have to solve this equation straight out, and that's what this does. I won't go through the calculus of actually doing the solving process. You can look in the notes to see a little bit more about that if you're interested. But suffice it to say that after, not a terrible amount of algebra, but a significant amount of algebra, you get this expression for the DNPP concentration as a function of time. And a couple of things are worth noting, pointing out. The first is that if I let time go to infinity here, so I let time get very big, then this whole exponential will go to 0, and this whole exponential will go to 0, and I'll just get that the DNPP concentration as time goes to infinity is equal to the piperidine concentration, the initial piperidine concentration divided by 2. You can see that, right? This is the only term that doesn't get killed as time goes to infinity. Is that correct? Well, that is correct, right? If the piperidine concentration is limiting anyway, then the amount of DNPP you get out at the end, the maximum you get out, is just half the piperidine concentration because 2 piperidines are used every time a DNPP is created. Another thing worth pointing out is that in these exponentials, there's this quantity right here. That is that initial piperidine concentration minus 2 times the initial DNCB concentration is an effective single concentration that goes into the equations both here and here, which means that if we put in twice as much piperidine initially as there was DNCB, in other words, if we put in stoichiometric amounts of DNCB, then this will be a 0, that will be a 0, and things will obviously simplify down quite a bit. That's one of our special cases, right? That's the stoichiometric special case. And you can see that it's a special case directly by looking into this general solution. You can also see it in other ways, but looking at the general solution is probably the simplest way. So here's the stoichiometric conditions. We put in twice as much piperidine, right, as there was initial DNCB. And in that case, if we solve things back out, if we go through this process of solving for the DNPP concentration versus time, we now get a much simpler expression. Our expression down here, up here, was pretty complicated, not terrible, but pretty complicated. Down here, it's much simpler. And if everything we've done so far is correct, then this much simpler expression should still fit the data when we're under the stoichiometric initial conditions case. The other case we can consider is the case where we put in a huge excess of piperidine. So the initial piperidine concentration is much greater than the initial DNCB concentration. In that case, when we've run out of DNCB, by the time all the DNCB has been used up, let's suppose we had 100 times excess of piperidine, the piperidine concentration is still at 99% of what it was to start with, right? The piperidine concentration has barely changed, even though we've run out completely of one of our reactants, and that will stop the reaction. So even at the end of the reaction, we've still got almost all the piperidine that we started with. If you use that approximation, then our rate equation for the formation of DNPP reduces down to a first-order equation, right? This now expression is approximately a constant because the piperidine concentration is approximately a constant. And that means that the DNPP concentration just depends to first power on the DNPP concentration itself. So we have a first-order reaction. We can solve that first-order differential equation fairly easily. And again, we get a much simpler expression than we would if we did the general case. It says now that the DNPP concentration is equal to the initial amount of DNCB that we have present times 1 minus e to the minus piperidine initial concentration times K1. Notice that this is sort of a K1 prime. This concentration, this constant concentration of piperidine times the true rate constant for K1 is playing the role as if it were a first-order rate constant in its own right. And in fact, you will see that this K1 prime, if you look at things, you'll see that this K1 prime has units of a first-order rate constant as well. So we've turned our second-order reaction by flooding one of the reactants. We've turned our second-order reaction into effectively a first-order reaction. And that's a useful and general thing you can do in a whole lot of chemical reactions. So one of the virtues of this whole lab is that it illustrates a lot of the sort of standard tricks that chemical kineticists use in order to analyze their reactions. All right. That's the theory and background behind the analysis or the model and analysis of the model for our chemical reaction for this week. What remains now is just to talk a little bit about what that means, what we're going to actually do with the data that we've collected. So what we've collected are runs of absorbance versus time. And so the very first thing we need to do is to convert those absorption recordings or measurements into concentration of DNPP. DNPP. versus time. And the way we're going to do that, it's not the best way. We really should do this better. If this were a real research project, we would do it better. But the way that we're going to do it for our purposes is just we looked at the data at 472 nanometers, and at 472 nanometers, the extinction coefficient is officially assumed to be known and is equal to 360 molars to the minus 1 centimeters to the minus 1. So absorbance is equal to the extinction coefficient times the concentration, dNpp, times the path length. The path length is 1 centimeter. That is now known, and so dNpp is equal to our measurement divided by our known extinction coefficient and then the path length. And so that's just a matter of doing the calculation on an Excel sheet. Then you need to calculate what the DNCB concentration, the initial DNCB concentration is, the initial pyridine concentration was, for each of the 5 special cases. For 3 of them, they'll be the same. For the other 2, they'll be different. Because those are inputs into our models. And then we're going to fit each of the curves. Now, these curves will now be dNpp versus time, and we're going to fit them to the appropriate model. There's 3 different models. The general case is the model that you use for the time-dependent data, right, for the 20, 40, and 60-degree data. Then there's the special fitting function for the stoichiometric case, and also the special fitting function for the flooding case. In those 2 cases, those 2 special cases, use both the general case fitting function and the special case fitting function, so you can compare how well the special cases do in each case. And then finally, once in every case, what your fitting the only parameter in your fitting function that isn't already known is the value of this rate constant, the K1 rate constant, which remember is the rate constant for the formation of the intermediate from 2 reactants, DNCB and PIP. And so fitting the data is going to give you a value of K1 in all 5 cases. We can compare those, for 3 of those cases are all at 20 degrees, or nearly 20 degrees. So you can compare the K1 value for those 3 different cases. You should get the same value, or very close to the same value, for all 3 of those cases that are at the same temperature. Then there are 2 other cases, the 40-degree case and the 60-degree case, and since rate constants depend on temperature, of course, you're going to get a different value of K1 for 40 degrees and 60 degrees. There's also a 20-degree case for the same set of conditions, so those 3 temperatures give you 3 different K1 values and you can use those to construct an Arrhenius plot. Remember that an Arrhenius plot is a logarithm of the rate constant versus 1 over the temperature. 1 over, not the degrees centigrade, obviously, but the degrees Kelvin temperature. So this is what? This is 293. This is 313, is that right? 323, and then 343. Is that right? Yeah, I think so. No, 313 and 333. Those are the Kelvin temperatures. I think that's right. 303, 313. Yeah, okay. And those are the temperatures that go along the x-axis here. And the slope of that curve then should be equal to minus the activation energy divided by R. Here's the Arrhenius expression. Here's the Arrhenius expression for the rate constant as a function of temperature. Energy of activation is assumed to be independent of temperature for this expression. The pre-exponential factor is also assumed to be independent of temperature. This expression isn't the very best one out there, but it's one that's very widely used because it's simple. An awful lot of times in science, people use simple expressions, even though they're known to be bad or not so great. because they're simple, because simplicity is its own virtue. If you take the logarithm of both sides of this equation, you get this expression, which is the expression that we're using in order to create the Arrhenius plot, right? This is the y-axis value, logarithm of k. This is the x-axis value. This is y equals mx plus b. That's b. This is m. And this is our x value. That's why we're plotting log k versus 1 over t. Plotting log k versus 1 over t should give a straight line if the Arrhenius expression is correct. It will give a curved line if the Arrhenius expression were wrong, but we've only got 3 temperatures in this case. We really can't tell whether we've got curvature or not in this case, so we're just going to assume that the Arrhenius expression is correct. And assuming that, we can make a least squares fit to our 3 data points, and the slope of that fit should be equal to minus EA over R. And so multiplying the slope times minus R should give us an estimate of the activation energy. I believe that the correct answer is somewhere in the neighborhood of 45 kilojoules per mole for the size of the activation barrier. Remember that the activation barrier is this, right? Here's the initial energy, here's the, for the reactants, here's the energy for the products, here's the barrier, the energy of activation is the height of that barrier, and it's about 45 kilojoules per mole. At least that's what both Amy and I got when we did this experiment. All right, well, I will talk more about this on Monday, tomorrow, and if there are questions, you can ask them then.